So this is our senior design project for Battlebots in the year of 2020. My name is Isabella Long. Our other team members are Fred Schroder and Mathew Itapson, who you will see shortly. So some background on a quick recap of our project. We were doing Battlebots, which is our project included the design and construction of a real-life fighting robot. We were going to compete in the Extreme Collegiate Clash Battlebots competition, which is a nationwide competition that's held twice a year. Unfortunately, due to the COVID-19 shutdowns, the competition was canceled and we were unable to attend for this reason. So in order to achieve building this robot, we had to devise a problem statement. So that problem statement was to design and build a combat robot to compete in this Extreme Collegiate Clash. So in order to achieve that, we actually needed to meet the regulations. We needed to be able to fight and disable other robots, and we needed to put on a cool show and really show how cool we are. So some of the major regulations, the most important one ultimately was that we needed to be 15 pounds or less. If we were any more, we would not be able to compete and we would have failed in our ultimate mission. It also had other rules, most of them for safety, such as using batteries that won't spray when damaged, or having an external deactivation switch.
So my main goal for the frame was to pick a design that complemented both the drivetrain and the weapon we selected. Our focus of the research was the box frame, the spinning frame, and the tripod frame. Box frame has an adaptable design. Spinning frame has added benefit of protecting the bot extra, and the tripod frame lets the weapon be elevated above other competitors. Armor will determine how the bot absorbs forces and where weak points are located. The struggle is to protect the bot while remaining machinable, undercost, and underweight. The most common armor materials are going to be steel, aluminum, and titanium. For this project, I got interested in plastics and researched ultra-high molecular weight polyethylene, which has a strength-to-weight ratio 8 to 15 times greater than steel. It's a great shock absorber, it's easily machined, and it's commonly used in low-weight competitions.
So there was a variety of weapon types that we researched, such as the vertical spinner, the horizontal spinner, the wedge, and the one that we eventually decided upon, which is the drum spinner. So the drum spinner, it doesn't really have a lot of weaknesses except for the fact that the inertia that it has and generates makes it very difficult to drive. But on the other hand, it has great offense and kind of doubles as a defensive weapon.
So wheel configuration is what kind of wheel setup we had. We had several options. We could either have done a two-wheel configuration, multi-wheel configuration, where it's just any configuration that's larger than 4, and a tread drive configuration. The kind of drive types we were looking at are the gear drive, belt drive, and chain drive. Each one provided power to the wheels, but with different levels of flexibility in location and size.
So for the state of the art, what we learned from past senior design teams, we like box frames with invertible drives. We like placing the electronics in a heavily armored area or adding extra armor to areas that were commonly damaged. What we didn't like was the frame being too bulky and impeding the weapon, not accounting for proper screw or weld bulk, or not being able to shave weight from the overall frame.
So for the weapon state of the art, our research based on past UC Battlebot years, the biggest things that I really learned were to keep the connections between the components simple so that there's not a lot of stress concentrations between where different parts are being matched up. And one of the biggest things too was to ensure that there was symmetry on all axes of the actual drum and tooth design, because without the symmetry component, the bot will actually shake itself to death with that large amounts of inertia generated by the weapon.
What we learned from previous years for the drive configuration is that keeping it as a two-wheel configuration and as a drivetrain, gear drive train, we could generate a lot of power in a very small amount of space while keeping the bot flexible and very quite fast. We were interested in using the brushless motor instead of a brushed, because the brushless offers greater vibration resistance versus the brushed. And here are the previous years bots that we learned from in order to create that state of the art. The end user for the Battlebot would be the Extreme Collegiate Clash 15-pound combat competition, as well as the judges, ourselves as the competitors, and our opponents. The customer features that we came up with came from research from the Collegiate Clash itself, surveys for veteran Battlebot club members, and from the Extreme Collegiate Clash rulebook. Our Battlebot design criteria, our most important criteria that we looked at for design is making sure that we were able to do damage to our opponents, as well as be able to protect ourselves from taking any damage. And part of that is being able to quickly evade or move around the battlefield. The customer features that we rated out of 5 came from our surveys. Some of our more important features were making sure that we met the weight, because that would disqualify us if we exceeded the 15-pound criteria, making sure that the bot was safe for usage. Some of our product objectives were making sure that the weight was balanced properly in order to make sure that we didn't throw ourselves off in competition, as well as making sure that the weight was correct. The other very important objective was making sure that our materials that we used for the bot were as optimized as possible in order to make sure we made the best quality bot.
So based on our research, we created 3 initial concept designs that satisfy the product objectives and the competition requirements to various levels. This first design here is a 2-wheel drive bot with a 45-degree wedge. It's equipped with a high-speed motor and heavy armor. Its objective is to flip over other bots and avoid taking hits, basically allowing other bots to break themselves. Historically, this wedge bot design is very successful in competition. It allows to last multiple fights. Negatively, it has low showmanship, low offensive capability, and the design is not reversible. Our second design was a 2-wheel drive 1-piece box frame drum spinner. The 2 wheels allow it to have a tight turn radius, and the wheels are large enough so it can drive if flipped or inverted. The large 1-piece aluminum frame adds extra structural strength and allows components to be placed out of harm's way, away from the walls. Disadvantage of this large frame is it's hard to make spare parts for. The drum spinner itself is an aggressive weapon that will attack other bots and will also protect the entire bot's front face because of its large weapon surface area. Disadvantage of the drum is it's heavy, it's expensive, and it has a complex design. Our third design is a 2-wheel drive multi-piece box frame drum spinner. It has the same weapon and drivetrain benefits, but the frame is a little lighter weight and more cost effective. The multi-piece frame is an aluminum skeleton held together with T-brackets with polyethylene armor over it. This way the armor will absorb the hits. Parts on this design are more easily replaced, and repair is more cost effective and material effective. However, there are more stress concentration points in this design. For design selection, to select one of the 3, we made a weighted matrix and comparing how well each design was able to meet the design criteria. Each design was broken down into its own sub-factor table. For example, offensive capability was broken down to weapon speed, weapon surface area, damage delivered, and weapon durability. These sub-factor scores were multiplied by weighted importance, and the weighted importance was gotten from our survey results and Battlebot's club members, and that resulted in a final score. All bots scored pretty similar with about a 9% difference in total. The wedge bot scored the highest in the 1-piece frame than the multi-piece frame. We decided against the wedge bot because we wanted the challenge of making a complex weapon system. So we designed both multi-piece frame designs and 1-piece frame designs. Ultimately, we went with the 1-piece design as the multi-piece frame failed to meet our needed strength requirements. So this is our previous design from Senior Design 2. We further refined this design to make it more weight effective, more cost effective, and more space effective, and simplified the design quite a bit. So here's our newest design. It weighs in total 13.94 pounds. It still has the one-piece polyethylene frame as from Senior Design 2. Dimensions were shrunk on the frame slightly, and the top plate was redesigned. The weapon dimensions were also shrunk, and the weight was reduced. It was also rebalanced and simplified quite a bit. The drivetrain has been redesigned to be more secure inside the bot. This bot still has a box frame with two-wheel direct drive and a single belt-driven drum spinner. This design scores high on defense, ease of manufacturing, and scored low on cost effectiveness and ease of repair, as the whole frame would need to be replaced if it is damaged pretty significantly. To negate the repair time, we did budget in 2 of every frame part. So the final design for the frame measures 12 by 8.5 inches on the exterior body and is 2.5 inches tall. The rear wall is 3/4 inch thick, and the front and side walls are 1/2 inch thick. The top cover is made of 90,06160 aluminum and is also recessed. We switched this from a UHMW top cover, as the UHMW top cover did not provide a stable enough base for us to secure parts to. The front skids will allow the bot to remain level with the 4-inch wheels, and it will also help in transferring force when the bots get hit, transfer the force into the ground. The skids have a 7/16 bolt running through them that will also secure the weapon to the bot. The rear orientation bolt has been added to make the bot less flippable. The internal storage space in this frame measures 7 by 7.5 inches, and its total weight is 3.64 pounds. So the UHMW polyethylene material was chosen for its great elasticity, durability, and low weight and ease of manufacturing. The one-piece frame design was chosen for its great strength to weight ratio, as with a one-piece frame, the force can be transferred over a larger continuous area, eliminate stress concentration points where the frame is susceptible to cracking, such as bolt holes or connection points. For frame calculation and testing, all the deflection and stress calculations were done using FEA and SolidWorks. First, we calculated the kinetic energy of a blow from a 1600 RPM 4.9 pound weapon based off an existing UC Battlebot. We converted this force into pounds per square inch and applied that to the bot. It calculated out to approximately 160 psi. For all the tests, we tested the worst case scenario of the bot stuck in a corner and immobilized. So overall, the frame tested between 13.6 and 5.26 safety factor. The worst performance on the frame was at the rear center, where a safety factor of 5.26 was calculated, and there was a deflection of 0.039 inches on the bottom lip. The most vulnerable point on our frame is the top and bottom plates. When we tested a hit here, the safety factor was 1.3, and there was a deflection of 0.067 inches. The stress calculations caused many iterations of the design. In total, there were 4 multi-piece designs and 3 one-piece designs that either failed to meet our desired strength or weight requirements.
So for the final design of the weapon, a lot of changes were made to simplify the design, to prevent stress concentrations, and to make the moment of inertia and the actual force delivered greater. So the materials were changed to what seems at face value to be a weaker type of steel and aluminum, but the change to 1020 carbon steel for the drum and teeth, this made it less expensive, which we were somewhat tight on budget, as well as still granting us the required shear modulus, which would resist the shearing during impact, which is the main load that we would be facing. The weight of the drum is about 5.18 pounds, so this is also about a 2-pound reduction in our weight. The aluminum shaft was changed from 70-75 aluminum to 60-61 aluminum, which was, upon further research, was discovered that the 60-61 was superior for its ductility properties and less likely to just shear outright, completely disabling our weapon. So inside of the drum are aluminum supports. These supports are also made out of 6061 aluminum. There are 3 of them. They're all about 3/4 of an inch. Inside you can see the bushings also, which support them. They're all held in place by 6 of the same type of countersunk screw. There are 3 on the top of each and 3 on the bottom underneath, which you can't see in this view. So it may seem like it's a weak point where the screws go into the plates, but this is not the case because the actual shearing force on those screws at those locations is only the amount that is resisting the motor turning and not actually the force of combat. For the drivetrain of the weapon, so the weapon is actually powered by a belt and pulley, similar to how it was before, this time using a timing belt instead of a grooved belt to give better contact and allow it to spin up faster. The complex tensioning system was replaced with a simpler C block, which using these slots can be adjusted forward or backward once the belt is over the pulleys in order to properly tension it, and using a nut and bolt through the block is able to be properly secured. As far as tests go, I used SolidWorks FEA as well. In order to simulate impacts, I used the drop test because SolidWorks doesn't have a better form of impact or shock tests in the regular version, and we didn't have enough room in our budget to purchase the additional software to make further impact tests. So using the drop tests, I found that it had about a safety factor of about 5.85 when considering the expected 300-pound force that we might expect. These images of the drop tests that I performed were on a 6-foot drop test, which is actually more like 2.5 times the expected force at about 861 impact force pounds, which resulted in a safety factor of only 2.04, but again, that was at a higher force than was expected. For the testing and calculations, as I said before, the impact force was based on using our own forces as a weapon, of what the weapon can deliver. I tested with different angles and heights of the drop tests to try and see and simulate what various angles of attack would do. Unfortunately, again, due to software limitations, there were only so many tests that I could do. But we were planning to do further testing later on, and that'll be gone into later.
For the final drivetrain design, not a lot has changed since the previous design. We've added a motor guard, 4 1032 screws, and a bronze bushing. The design is fairly simple. The idea is to keep the drive system elevated so that the wheels are capable of running on either side if the bot is ever flipped. The motor guard was added to add protection to the motor, screws to keep it in place, and the bushing to protect it from the side of the wall. Since we did not change the motor or the drive, the gearbox, the drive calculations stay very much the same. We did test against using the RS500 motor versus the D2826, but with our calculations we found that the only difference would be instead of getting 17.37 miles per hour speed, we get 13.4 miles per hour, and we decided that having a faster bot during the battle would be more important than having a slower one. Because the configuration of the motors and the batteries stays the same, the electronic configuration and control scheme stays the same from the previous design. We also have an LED here as a requirement by the Extreme Collegiate Clash competition.
For the planned frame fabrication, all the fabrication can be done at the VPC North Laboratory free of charge. 2 of every frame component was purchased, so a future team can make a spare frame. The UHMW body was ordered in a raw block. First, the frame profile will have to be cut out of this block, and the exterior holes drilled, and then the center cut will be made. For cutting the profile, it will be cut with a bandsaw, and the exterior holes will be drilled using a drill press and a low flute bit that is appropriate for cutting plastic. This low flute bit may need to be purchased if not available at the laboratory. For the center cut, 4 holes will be drilled in the corner, a bandsaw threaded through those holes, and the center cut made. Recessing of the top cover will be done on the CNC machine before the center cut is made. For assembly, screw inserts should be placed inside the top cover holes, punched into them, and then screws and bolts fastened where noted. For the aluminum cover plates, a large sheet of 6061 aluminum was purchased that will make 4 cover plates in total. The profile of these plates will be cut on a plasma cutting machine. For hole placement, a 1-to-1 paper template will be printed out and glued to the profile, and the holes drilled where located using the appropriate diameter bits. For the slots on the top cover, they will be drilled as holes and then widened using a Dremel. For the skids, the bottom of the skids are made out of scrap UHMW. These skids will be cut from scrap material using a bandsaw and then shaped to the approximate dimensions using either a lathe or a belt sander. There is an alternate method of mounting the skids that gets rid of the bolt, in which case the inside of the skid is threaded. That will need to be done if this method of mounting is chosen. The 4-inch skid bolt will need to be cut from a 3-inch length of all-thread rod or 3-foot length of all-thread rod. And lastly, there is reinforcement armor that is possible if a future team has spare weight. This would be to strengthen the weak areas and probably made out of the scrap aluminum. Weak points on the bot will be determined from strength testing, and the armor dimensions will be dependent on how much spare weight there is. All of the armor should be able to be cut with a plasma cutter, a bandsaw, a drill press, and then secured to the bot using wood screws.
For the fabrication of the weapon, prior to the COVID-19 shutdowns, I was able to complete some of the machining on the drum weapon. First, I cut these segments to length using a bandsaw, then they were faced to length to achieve a smooth finish, surface finish on the ends, and finally they were milled to achieve those half-inch grooves that you see there where the teeth will eventually be welded in place. Plans for future manufacturing were to mill in the initial screw holes in the using an 82-degree end mill to prepare for the countersunk screws. The aluminum plates after that point would be milled out of flat plate using a CNC machine, eventually sanded to size, sanded to get that final dimension and press fit inside. Once in place, the rest of the screw holes were to be machined in using an 5/32 end mill. That way that the location of the drum hole, the holes in the drum and the holes in the aluminum would be in the same spot, allowing those screws to go in. The motor support C block was to be, the slots were to be milled first, then the actual C shape out of it. The drum shaft was to be purchased at the correct outer diameter. The holes for the frame would be milled in using an end mill, and then finally tapped. The pulley for the drum, again, would be milled out with an end mill, and then have tack welds onto the side aluminum plates. The welding of the aluminum was originally a concern, but we have a team member that was willing to help with this that's previously done aluminum welding and was very generous in allowing us to have help with that.
For the most part, the drivetrain parts come ordered online with the fabrication already completed. But for the 2 parts that we made ourselves, some design needed to be done. The fabrication plan for the motor guard was fairly simple. I drew up the design plan in SolidWorks, and then I would have brought it over to the 1819 building to have it 3D printed. Because of the size of the motor guard as well as the size of the 3D printing table, we could have had both the left and right side motor guards printed at the same time to save on printing time and save on costs. As for the support blocks, there's a slight design change between over time. We were initially having support blocks made out of 3D printed material, but it's decided that wasn't as safe as using the frame material. So the fabrication plan for the support blocks became taking the spare material from the frame and recutting it at the VPC with the bandsaw to get it to the right size, as well as use the low flute drill bit to cut out the holes for the 1032 screws. After getting those parts fabricated, all that was left is doing a final assembly, which is mostly just putting them all together. So we also have some animation for the weapon. As you can see, we have the drum actually rotating. This is a simulation for how we would expect it to move. We also have a simulation expectation of how it would do in combat. We would expect that it would launch the opposing bot a little bit higher, a little bit faster, but we decided to slow it down in order so you could show, you could actually see how the impact would affect the opposite bot.
So for the recommended frame testing, using spare UHMW polyethylene, a 1/2 inch and a 3/4 inch plate will be cut. This mimics the size of the bot's walls. This plate will be secured in a vise and then tested against an existing Battlebot in the club's combat arena. It will be tested until it breaks. This way, a future team can have perspective on how much damage the bot walls can take in competition. If this test goes well and significant damage is tested, I recommend testing the spare frame against an existing Battlebot. Have the bot hit that once and then observe the frame for any deformations, and this will determine where any reinforcements are needed if you have that weight to spare. Once the weapon test is finished, I would recommend examining the weapon attachment points. If any attachment point is loose, it may need to be rethreaded, tightened, or glued in, and then retested until satisfactory results are achieved. Lastly, I'd recommend doing an orientation test. This is just making sure the bot lands upright if it's placed in any sort of orientation. The orientation bolt length at the rear of the bot may need to be adjusted if it does not land upright.
In order to test the weapon, I recommend testing it against a section of polyethylene that's left over from the machining process of the frame. After that point, I'd like to compare that results of that to the weapon of the legacy bot Jeff's against a similar section of the frame, about the same thickness, and see which one does more or less damage. If we're similar or doing better than the bot that has done well in previous years, then we should be in the clear. And then additionally, I would like to do a drop test on the full assembly in order to confirm the results from the earlier testing.
So for the planned testing for the drivetrain, I'd recommend doing a complete assembly for just the drivetrain, testing out how all of the parts function together, making sure that it all fits inside of itself smoothly, and that the wheel can rotate at the speeds that it needs to for the competition. While it is still just the assembly for the drivetrain, I'd also like to do a drop test to make sure that it can survive the impact from similar forces that it will be taking during the competition. And then finally, when the bot has been fully assembled, just comparing the speeds that it can reach versus that of the previous bot and Jeff to make sure that we are at a level that is battle ready.
So for the frame battle expectations, I expect it to be able to sustain multiple blows and last multiple rounds before it needs replacement, having a safety factor of 13.6 to 5.26. In the best case scenario, we would face a wedge bot or a spinner of similar dimensions to us, and all blows would be received on the frame. Most ideally, it would be received on the corners, as those are the strongest. Ideally, the frame would protect the internals long enough for us to disable the other bot, and there would also be ample replacement time in between rounds to make any repairs to a damaged frame. Worst case scenario, we would face a hammer bot, or the frame would get oriented in such a way where it receives a direct hit on the top plate. This would do on our bot pretty quickly. Also, if we were immobilized, it'd be unideal if we were repeatedly hit in the same location. And lastly, it'd be unideal if we had less than 30 minutes repair time and we had to replace the entire frame, as I think this would be pretty difficult.
For the battle expectations of the weapon, the best case scenario would be that with every hit, the opponent is knocked high into the air by the weapon, and thus they would take extra damage from the force of gravity. A fast spin-up time in the initial start, critical first seconds of the round, would also help us in defense capabilities, since once our weapon is up to speed, it helps prevent hits from getting in and actually deals damage at any attacking point. The worst case scenario would be that the welds could fail, the teeth could fall or could shear off. It's during hits, and possibly the belt and pulley system. The pulley welds could shear off as well. Any kind of deformation between the aluminum plates could possibly cause the weapon to become deformed to the point where it no longer spins properly. Another worst case scenario would be that the electronics may burn out. This is unlikely, but especially since most matches don't typically last the full allotted 3 minutes, but it's still possible that they could burn out, and that would prevent us from being able to engage in further rounds as well.
So for the battle expectations for the drivetrain, the best case scenario is that we succeed in making a very fast, very agile bot that can dodge attacks from opponents. Very adaptable in being able to be hit, flipped upside down, and still run. We'd also like to be in a scenario where the motor becomes disabled, the motor of the weapon, gets disabled, and being fast enough to ram into the enemy bot and still do some amount of damage, and to be able to stay in the fight, in the worst case for the weapon. And would be great for the drivetrain would be having the batteries survive the entire 3 minutes of the battle without drops of power causing drops of performances. The worst case scenario for the drivetrain would be that the batteries do not last us the entire combat, or that they combust, or that the internal electronics combust. This would disable our bot for the entirety of the competition, for the entirety of the combat, and disqualify us from the competition. Another potential worst case scenario would be that the gearbox shaft gets damaged. This would disable either the left or right side of the drivetrain, making it difficult to control it and disqualifying us, as controlled movement would not be possible in those scenarios. It'd be especially bad if either of those, if the gearbox gets damaged because we did not get a replacement with that. So if we lose the ones that we have inside the bot, then that would be it for the competition.
This is the proposed budget that was ultimately approved. In the approval stages, that we were approved for $1,200. As you can see, we kept under that to some extent. This whole full budget includes a spare frame and armor, spare full weapon assembly without including the electronics and the internals, and then also general components were included in this. If we had had a larger budget, we would have probably gone back and purchased more drivetrain parts, such as the gearbox that was mentioned before as an important component. As far as the actual budget, unfortunately due to COVID-19, after purchasing the McMaster-Carr parts, we halted our other orders, and so we only actually purchased $363 worth of parts. So if a future team was to complete the building of our bot, they would have to purchase the other components we listed in our bill of materials in our report.
So we had a proposed schedule previously in the semester. We had accounted for The materials being approved when they got approved, as well as machining time and assembly time and testing time. We had given ourselves a week after the orders had been approved to receive the parts, as well as a week to do the machining and assembly. The assembly time contradicted slightly with the Tech Expo. The plan there was to use as much time as possible to assemble the bot before the Tech Expo, and then if there was anything that had been left over, we would have used the extra day afterwards to make sure we were up to code as much as possible. The following week we would have used to do testing. It would have included all the drop testing and full configuration testing, as well as comparisons. This would have led us up until the final testing for the competition, and then into the competition. The following week we would have had our presentation, and the final report would have been submitted. Unfortunately, that got disrupted slightly due to the COVID-19. So we had to adjust the schedule and our plannings. We still accounted for the materials being ordered and for the ones that we received. However, we had to switch to virtual testing and some theorized fabrication. We still came out ahead of the presentation and the final report.
So our final recommendations for future senior design team in general are, in the design phases, we recommend discussing the fine details of the design with club members. They provide us with valuable advice that heavily influence our design. We recommend to stop making changes at a certain point in the design, have a deadline for this, as we made late changes and it pushed our schedule back. We recommend designing in 1 to 2 pounds of spare weight, as insulation and wiring weighs a bit more than we initially expected, so design that in initially. In budgeting, budget conservatively. Money has the habit of disappearing. Know which parts you would cut if your budget does get reduced. I recommend doing this by prioritizing duplicates. Know what needs to be a duplicate based off of how often it breaks. Battlebot's club members can advise you on this. And most importantly, get all your components selected, approved, and ordered as soon as possible. This was the biggest hindrance to our schedule, was the pushing out of the state. For fabrication and testing, recommend starting early, of course. Do this by having your parts ordered early, back to that one. And discuss your design with VPC North Laboratory Manufacturing Advisors. They will let you know what design changes you need to have to make it manufacturable, and if you need to order any additional tools. Thank you very much. That is our presentation. Please let us know if you have any questions. You can reach us by email.